Hi everybody. During this course, we are going to be covering the various methods that are used for statically indeterminate structures by Dr. Abdulkareem. Let us start off. Start off with the contents of the course, which including various methods to calculate the deflection and rotation of various structures, which are required to analyze the intermediate structures. This is what we'll see when we get to lectures of statically indeterminate structure. The first method to calculate the deflection and rotation of structure by using virtual work method. We are going to use this method to calculate the deflection and rotation of beams, frames, and trusses. Let us start off with the deflection and rotation of beams. This lesson, the method of virtual work is used under different loading conditions on different boundary conditions. The following example explains the steps to be followed to calculate the deflection and rotation of statically indeterminate structure using this method. Example: determine the virtual displacement and the slope at the end point C of the cantilever beam, which is fixed at support A as shown in the figure below. The modulus of elasticity E and the moment of inertia are constant for the entire beam. The explanation of the method will be in steps to make the method easier to understand. First, apply the equation of virtual work to determine the desired displacement delta or rotation theta as below. First, to find the deflection of the beam, if we see the equation 1 means the unit load times deflection. As we see, load times deflection is equal to the work, and that is why it is called virtual work method. Equal to integration from 0 to L, length of the beam, M small is the moment due to unit load applied in the direction of the required displacement, as we will see in the example. M capital, moment due to external force. EI, textural rigidity, taking as constant. E, modulus of elasticity. I, moment of inertia of the beam. The second equation for rotation or slope as below. 1 times theta for the slope equal to the integration from 0 to L m small theta unit moment at the point we want to find the rotation. Here is unit moment, before was moment due to unit load. Now is moment due to unit moment. M capital theta, moment due to external force. Now we will see how to apply this equation to our example. First, to find the deflection at point C. First, we remove all external loads on beam. And here is the external load 2B. Then we will apply unit load at point C, the point where we want to determine the displacement. Then we take section X as shown in the figure from point C, and we will cut the beam at a distance X from point C. We take X from right to left to avoid calculating reaction at point A. So it is not required to calculate the reaction. So we take the cut from C to O. Then we apply equilibrium equation at point O. We'll take the moment at point O. Clockwise will be the positive moment. If we take the moment at point O, m small plus 1, the load, times x, the distance, is equal to 0. So m small is equal minus x. Now we will find the moment due to external load 2P, and this will be capital M. We will take 2 cuts before 2B and after 2B. Before when we find M small, we see we'll took only 1 cut because there is a unit load at point C and the moment will be constant along the beam L. But here we will take 2 cuts, first cut before the load and the second cut after the load. Trusses M1 will be 0 here because there is no load at point C or between point C and the load 2P. So the first cut, M1, there is no load here, so M1 is equal to 0 when we take moment about point O. For M2, when we take moment about O and the positive direction of the moment is clockwise, so it will be M2 plus 2B, the distance for the 2B, x2 minus L over 2, and this will be equal to 0. So M2 will be minus 2B x2 minus L over 2, then M2 minus 2B times x2 will be minus 2bx minus 2b times minus L over 2 will be plus PL. Then we will find the deflection at point C as per previous equation will be equal from 0 to L over 2 plus integration from L over 2 to L. The value of M1 is equal to 0, so the first integration will be 0 and the second integration will be M1 small minus x over 2 as we find before, M1 capital minus 2px plus PL over EI. As we know, the integration for x to the power n is equal x to the power n plus 1 over n plus 1. So the integration for x to the power 2 is equal x to the power 3 over 3 times 2b minus PL x to the power 2 over 2 from L over 2 to L. Then we will substitute x with the value L first minus x with the value L over 2. After that, we will find the deflection will be 5p L to the power 3 over 24 EI. The value of the deflection is positive, so it will be downward as we assume. Now we find the rotation of the beam at point C for the same beam. First, we will apply the equation of virtual work to determine the desired rotation theta as below. 1 times theta equal to the integration m small theta, the unit moment, m capital theta, the external moment, over AI. Second, apply the unit moment m small at point C and follow the procedure used previously. After we apply the unit moment at C, the point where we want to find the rotation, we will take cut at a distance x from the beam, and we will take then a moment about point O. So the moment at O equal to 0, m small plus 1 equal to 0, so m1 equal minus 1. Then we will find the moment m due to external load. m1 equal to 0 moment about O, m2 equal to minus p times x minus L over 2. Then we will take the integration from 0 to L over 2, which equal to 0, because m1 is equal to 0, plus the integration from L over 2 to L. Then theta C will equal to integration m small theta 2 multiply m capital theta 2 over E I. After the integration as indicated above, theta C is equal to P L to the power 2 over 4 EI. Since the result is positive, means rotation is clockwise as assumed.